Okay, hi everyone. I'm Khooyooz, and today I'm gonna present my paper in EMBC Conference 2024 titled A Novel Machine Learning-Based Noise Detection Method for Photoplethysmography Signals. I've written this paper with my colleagues Jahanjoo, Aminifar, and Taherinejad in Heidelberg University, Germany, and Technical University of Vienna, Austria. All right. The outline of this presentation would be an introduction to wearable healthcare devices, a short review of the dataset that we have used for this research, and our methodology, evaluation of the results, and finally we conclude the paper. So wearable healthcare devices have different applications. Their main application is continuous health monitoring via physiological parameters and activity levels, and they are used for early detection of health issues. However, they have several design challenges and concerns. The first one is data. Data quality in terms of accuracy and reliability is always a concern and challenge when designing wearable healthcare devices. And data privacy and security is also another concern. There are also other concerns like battery life, uh, dimensions, and users' comfort, and so on. Cost and accessibility, durability, user interface, and so on. In this presentation and research, our main focus is data reliability. So, false alarm, false positives, what are they? It may also has happened to you that your wearable devices or your mobile phone has sent a wrong message or a wrong notification to you regarding your health condition, which sometimes is kind of stressful, sometimes it's annoying, sometimes you may ignore them. Therefore, these false alarms and false positives will cause unnecessary stress and anxiety, and they will cause medication errors and adverse effects, and gradually the trust of the users may be lost to these wearable devices, and there will be reluctance in using them. So what is the solution to solve this problem? How can we reduce the false alarms? We would say, how about starting with detection of corrupted parts of this data or the signals? There are different type of noise or artifact corrupting the signals. In wearable healthcare devices, two main type of them is motion artifact and baseline wonder. So motion artifacts, I will activate my pen here so that I can show you better here. So motion artifact in this signal is this part, which you would have your normal signal and suddenly something happens which is not interpretable more. So this is happening because of, for example, a sudden movement or a muscle artifact and so on. And the other types are baseline wonders, which are happening because of inappropriate electrode contact or sweating or like imperfections in design of electrodes and so on. And they will cause these type of kind of biasing in the signal, as you can see there. All right, so as we said in previous slide, how about starting with detection of corrupted parts of the signal? So we want to detect these corrupted parts or these biases in the signals, and kind of remove these part of signal and do the predictions based on the clean parts of the signal. And in this case, maybe we say, if this is the signal that is kind of corrupting the signal, we remove this so that we can get a normal signal like this. Okay. So let's do the predictions using the clean parts of the signal, as we mentioned. The block diagram of our presentation, our research is as this. We will have a data set. The data set probably includes some non-informative data. You will see later. We have 89 healthy student colleagues in actually between them 67 of them were usable, and we pre-process the data, and thereafter we have to annotate the signal to kind of motion artifact corrupted, baseline wonder corrupted, and clean signals. And after annotating the signals, we segment them to 20-second signal windows and extract features which are kind of representative of the segments, but have need shorter memory to be saved. And then thereafter, we input these features to ML models and do the evaluations. All right. So the data set is an open source data set on emotion, cognition, sleep, and multimodal physiological signals. It's for 89 healthy college students. The data has been recorded during resting state, emotion induction, cognitive function assessment. And each data's duration is about 1 hour and a half. And it includes EEG, electroencephalography, ECG, electrocardiography. The data recorded with Empirica E4 watch, which is a research watch, and includes PPG, acceleration, temperature, and electrodermal activity signals. And finally, we only use these two signals for our research, and we filter this signal with an fourth order IIR high pass filter with a cutoff frequency of 0.5 hertz. Okay. So for the signal annotation, as we mentioned, we only use PPG and acceleration data, which are recorded simultaneously, and we use the acceleration data as a reference for detecting motion artifact. The acceleration data is actually consisting of 3-axis acceleration data, but for simplicity, we only use one dimension, which is the SQRT of the squared signals in the 3-axis. And thereafter, we calculate the energy of difference of the acceleration signal, as you can see here, and we use it as our reference. And using a threshold, which we will define here, we create a binary signal, which is either 1 or 0, to use it for annotation of this signal. So this threshold is an average over all the data that we have multiplied by 0.5. As you can see here, we have used the binary signal, which is something like this. And it is 0 in these parts, and it's 0 in these, it's 1 in these parts. And so it means in these colored parts, the energy of the acceleration signal is higher than the other parts, which are 0. And this shows the in these colored parts, the PPG signal is corrupted by motion artifact. Therefore, we annotate this as MA corrupted and annotate these parts as clean parts. You can see the results. This is for those regions that we have 0, and this is for those regions that we have 1. And as we do not have a baseline wander reference in the data set, so we use the literature and find some characteristics in the literature for baseline wander signals. As you can see here, there were different characteristics, so we use kind of both of them for defining the baseline wander signals. And after creating the baseline wander signal, this is a clean signal, and this is a synthesized baseline wander. We add them up together to get such a baseline wander corrupted PPG signal. Okay, so for feature extraction, we we use morphological features, which are the time intervals between the location of peaks. Using Vital SQI library in Python, we calculate the location of the peaks in the signals, all of the signals, as you can see here. And the time interval between these peaks is saved in some arrays or lists and will be sorted based on the from maximum to minimum, and it would be considered as morphological features. And for statistical features, we use kurtosis, skewness, energy, entropy, maximum autocorrelation, and average and standard deviation of the histograms as the statistical features. Next, we will concatenate these features, and to make them kind of comparable together, we normalize the feature vector that has been created. For evaluation, we use the famous metrics in the literature like F1 score, accuracy, precision, and recall. And different machine learning models like SVM, RF, XGB, NB, ERT, and decision trees. And our criteria are binary and 3 classes classification, leave one out, cross-validation, and data balance. So as we mentioned earlier, so we annotated our signals, and in the first round, we trained the ML models with the labels. And in the second round, for evaluating and calculating the accuracy of one score and so on of the ML models, we use the test features, and we kind of evaluate the ML models. So as you can see here, I have shown the results for different type of classifications. The first one is clean versus motion artifact corrupted signals, which has achieved 97% accuracy. In the second one, which is clean versus baseline wander corrupted signals, 93% accuracy is achieved. As you can see here, in these three graphs. We have two set of graphs, which is because we had two type of baseline wonder. And as you can see, they are slightly different, but the trend for all of them is similar. And the highest accuracy is achieved via this motion artifact versus baseline wonder. And we also have performed a three-class classification for clean versus motion artifact versus baseline wonder, which is 89%. Okay, so another thing to mention is like the highest results for this classification are achieved using ERT and XGB models, which shows the high capability of these models to use in such a context. So as for conclusion, we detected the corrupted parts of PPG signals using machine learning, and ERT and XGB models outperform other machine learning methods and models. And one can use suitable filtering methods after detecting the corrupted parts of the signals instead of removing them. Probably if those parts which are corrupted are including important information, one can, instead of removing them, apply suitable filtering for baseline wonder removal or for motion artifact removal. But in the first, without recognition of the type of signal, it's not probably possible to blindly apply a noise removal method. And the fourth conclusion is we suggested a method for improvement of wearable device functionality by decreasing false positives. Thank you very much for watching this video and for your attention. This is the QR code for reaching to the paper PDF. And if you have questions, you can email me and I will answer you. This is my reference that I've used for this presentation. Thank you very much. Have a nice time.